So thank you for sticking it out through the long day and coming to the last session. Appreciate it. I'm Nick Principe from Dell EMC. I'll be presenting with Jig Bhadaliya, also from Dell EMC. Just a quick background. I'm just principal software engineer. I've been doing NAS performance for my entire career at EMC and now Dell EMC. Oh, there you go.
I've been with EMC for about 4 years now. Prior to that, I came from Broadcom, and I started with Rockwell Semiconductors in the 90s. So I spent over 15 some years in semiconductor space.
So Jig is a real EDA expert and brought a lot to the table here for SPEC and for the community. And today we're going to be introducing the EDA Workload as a new workload for the SFS 2014 benchmark suite. We'll talk availability later. We just want to introduce the idea and let everyone know that it's coming in our next release. So today I'm going to give a quick intro to SFS 2014 for any of you not familiar. And then Jig will take over and talk about what exactly EDA is and the characteristics of EDA workloads. And I'll walk you through, he'll walk you through some trace data from real EDA environments, and I'll walk through how we defined the EDA workload in the SFS 2014 benchmark. And I do have some example data for you. I wasn't sure I would. If you have the deck right now, we'll update it. I don't think the one on the has the example data, the one you can download now. So we'll get that updated. And then there are a few more enhancements that will actually come into the SFS 2014 load generator as part of the update that'll include EDA. So I'll cover those as well. What is SPEC? If you're not familiar, it's the Standard Performance Evaluation Corporation, which is a nonprofit established to produce industry standard benchmarks, and probably most famous for SPEC CPU, I would say. But we have a whole suite of benchmarks for different products and industry interests. Quick disclaimer, we're going to be talking about SFS 2014 SP2 and the EDA workload, which is part of that. And right now this is pre-release software, so everything in here is subject to change because everything's still under review and test. So a quick overview of SFS 2014. It is an industry standard storage solution benchmark. The whole lineage was an NFS server benchmark. In 2008, we expanded to CIFS and NFS, and with 2014, we expanded to testing whole storage solutions. In 2014, we also branched out and added 4 workloads instead of just a workload per protocol. So we started with the database workload, the software build workload, VDA and VDI, and now in SP2 we will be adding the EDA workload. SFS 2014 measures performance at the application level. So it does, unlike previous versions, if you're familiar with that, it doesn't generate its own protocol packets. It actually goes through your operating system all the way to the final destination. So it engages the whole storage stack from application to disk. Although if you have enough cache somewhere in your storage stack, it won't make it to disk. That's the beauty of it. But it does test your storage solution all the way from what your application would see, which we feel is much more relevant to customers because they want to know what their application performance will be. And because we have this flexibility and we're not generating our own, packets on the wire, we can test a much broader range of products configurations. So you can think of this as, regular hard disks, multi-tier hybrid arrays, and all flash, but you can also think cloud storage. Someone just did a test and actually got it running in Amazon, believe it or not. And we have published results now, and my colleague from IBM has published results on GPFS. So this is not just a NAS benchmark anymore. You can test any fully featured file system. And I sit here wondering after this whole week, I'm like, so what about these ones that are almost POSIX? I bet some of the workloads will run fine on that, but I haven't tested that. That would be cool. So for a more extensive introduction to SFS 2014, we actually do have video recordings on the spec.org link or the YouTube link, and the slide decks are also available publicly from SNIA. So there's one session that Spencer and I did from 2014 and one that Vernon and I did from 2015. So I encourage you to view those if you weren't able to attend. So now I'm going to hand it over to Jig, and he's going to talk about exactly what EDA is.
So how many have heard of EDA? Okay. So if you haven't heard of it, it's okay. And the word or the acronym itself is not that important. It loosely represents a large number of things, right? The acronym itself stands for Electronic Design Automation. But the way the word EDA is used to characterize a group of companies as well as a number of tools. So you can think of it as representing semiconductor companies. You can think of it as representing companies that actually manufacture chips, or you can even think of it as companies that develop EDA tools or applications with it, right? So, you know, if we go line by line here, bullet by bullet, it represents software tools and workflows that are used in designing semiconductor chips. There is arguably over 100-some tools, and it will take easily over dozens of tools to design a chip from its specification to fabrication. It's a compute-intensive process, and the compute grid has evolved from just having, you know, RISC-based processors to having thousands and thousands of cores that are x86 based, right? So it's a compute-intensive process, and the amount of concurrency required has increased over time as the technology node has shrunk to nanometer geometries. Storage is often the bottleneck, as the compute grid relies heavily on all data sets residing on NAS. So it's a shared storage infrastructure. All the nodes on the compute grid are uniformly configured to access all the data sets, such as projects, Scratch, tools, home directories, so on and so forth. So more often than not, you know, it's the file system and the protocol stack that becomes the bottleneck. If you were to look at the data set characteristics, the data set consists of millions of small files. This is because if you think about the EDA chip design flow, somebody decided that they're going to represent a circuit as a flat ASCII text file, and represent another circuit as another file, another circuit as another file, so on and so forth, and create a POSIX directory hierarchy to define a block and bigger block, and then ultimately a chip, right? So it is the unstructured nature of the directory hierarchy and the way the chip is defined that results in millions to billions of small files. There is a small percentage of large files. The large files can be as large as hundreds of gigs, right? The end result is stored in a standard format called GDS2, and that GDS2 file represents your image of the chip that you send out to the foundry to be manufactured. And so there is a small percentage of large files. The characteristics of the I/O are mixed and sequential, right? So mixed, random, and sequential, right? So as you go through various design phases, you have both sequential I/O for the larger files and random I/O for the overall smaller files. What we did is we divided up the design phases into two high-level design phases, front-end design and back-end design. This is how it's actually carried out and known in the industry as well. And what we're going to do is we're going to represent the workload and the storage characteristics of the workload by associating with the high-level design phases as well. The front-end design phases is where you have millions of small files. The back-end design phases is where you get the larger files. The front-end design phases does generate a lot of transient data known as scratch data. And the scratch data in the EDA space, unlike HPC, is actually stored on a NAS, right? So a traditional HPC, what you would find is that traditional HPC compute grid will have some kind of an interconnect, will have some kind of a distributed file system across it. But traditional EDA is, all the data, including the scratch data, is on a NAS system. You have lots and lots of jobs running concurrently. I've heard numbers anywhere from hundreds of thousands to millions of jobs per day. A lot of the front-end jobs, and when I say front-end and back-end, I don't mean front-end and back-end in terms of storage, right? I mean front-end and back-end in terms of the EDA chip design flow. The front-end workflow, the jobs run only for 2 to 3 minutes, right? A single job can run for less than a minute sometimes, maybe a few minutes. And the back-end jobs can run for hours, right? On the next slide here, I'll give you some more details into the workflow itself. But that's kind of the high-level idea. Because of the deep and wide directory structure, the workload tends to be namespace or metadata intensive. And you'll see some of that factored in as we define the workflow. Any questions as I go along? So here's the details in terms of the workflow. You will see a similar chart like this if you were to Google for EDA chip design workflow, right? But I'll step you through it quickly, and then I'll tie it into some of the storage characteristics, right? So I'll use a simple example of an adder. Let's say you're trying to design an adder. So that's your design specification. It's that you want to design an adder. Design is captured in what's known as RTL. RTL stands for register transfer level, I think. But in any case, it's essentially representation of your circuit in a hardware description language, right? Either Verilog or VHDL. It's tiny in terms of size, just as I was telling you on the previous slide. It's essentially represented in a flat ASCII text file in a high-level programming language, right? After that, you say, okay, I have described an adder, then I'm going to make sure I actually get that to functionally work as designed. So I would say 2 plus 2 and I anticipate 4. I would say 2 plus 3 and I anticipate 5. So it goes through a functional verification stage. Then you synthesize the design. Synthesis could be either on the back end or the front end. But think of synthesis as now bringing the design to the gate level, right? You're compiling your design. You're compiling your design against a given set of standard libraries, standard cell libraries that the foundries give you, like TSMCs of the world. These are the manufacturers of the chip, right? So once you compile the design, there is more due diligence to be done. Laws of physics kick in, and you would need to do timing analysis, right? If you had, I simplified it and I said adder, but if you had cascaded blocks in your complex chip, then it's important that block A feeding into block B is not delayed. So that's where timing analysis comes in. A place and route is optimally using a given set of die size to optimally place all your blocks for heat characteristics as well as timing characteristics. Extraction refers to the fact that even the interconnects matter, right? If you were in the earlier days, like in the 90s, this wasn't as big of a deal, but as the chips got smaller and smaller to nanometer geometries, even the wiring in between the blocks matters, and the resistance or the capacitance that it may induce could have an ill effect on your overall intended results, right, or expected results. So there is a workflow known as extraction or parasitic extraction. You then do physical verification and sign off, and then you eventually tape out the chip to the foundry, right? So these are, at a high level, these are kind of the workflows. You can see, a lot of loops going back, right? So it isn't necessarily sequential in nature. There's a lot of going back and forth from one design team to another. High level folks like to think of it in a sequential manner, but it's not necessarily sequential, right? And then if we zoom out even further, again, we're going to stick with the front-end design and the back-end design theme. And from a storage perspective, it works out well because the front-end design is where you're going to run hundreds to thousands of jobs concurrently, right? Because there's no such thing as a fully verified chip, right? You do the best due diligence you can, which is why Yes. Yes, you are running against the same set of block and running different corners, as they call it, right? Which essentially just means, just as I was telling you, if it was an adder, you would say 2 plus 2, 2 plus 3, 2 plus 4. So those are different iterations that you're going to run through the same block, right? And so that's, you go through that type of a phase, which is what induces the high levels of concurrency, right? Physical design is where, like for example, timing analysis. An output file for timing analysis could be as large as 26 gig, right? I've seen examples of output files of, there's a specific application called PrimeTime. This application generates large files. And so essentially you have a mix of small and large files. Of course, the number of jobs that you run is much less in the back-end design flows compared to the front-end design flows. You're looking at a magnitude of hundreds to thousands of jobs for front-end design. You're looking at a magnitude of tens to hundreds for the back-end design flow, to give you kind of a perspective. Clear so far in terms of how we're approaching this? As you look at this, one of the things to keep in mind is it's rather complex. There's many tools. There's many workflows. The way the data is allocated by the storage admin doesn't take into account any of these things. They essentially just say, okay, here's a chip underscore FE for all your front-end work, or chip underscore timing analysis, or STA. Static timing analysis, right? So, there isn't a lot of due diligence done at the time the storage is allocated. And as a result, what the NAS is seeing is kind of a mix of all these activities. And combine that with the fact that a house like Broadcom or a large semiconductor house may be working on tens of chips simultaneously, right? So you really have kind of a hodgepodge of things happening against the NAS, right? So this is the way to think of it, right? This captures what I was trying to tell you, right? Think of this as the EDA Compute Grid. The EDA Compute Grid consisting of tens of thousands of cores today. Someone like Intel would have 50,000 cores, right? It wouldn't be uncommon for someone of Intel scale to have 50,000 cores in their HPC Compute Grid, right? Start here, tool 1 through tool n. As I alluded to earlier, you could have over a dozen some tools. Then each one of those tools, if you have a certain type of an input to that tool, you have a job, and that job will have certain type of I/O characteristics. So you couldn't necessarily even say, I'm going to take application 1 through application 50 and look at the I/O profiles for each application, because depending on what you input to the application, your output and your I/O profile is going to be different, right? So you have a large number of I/O profiles that are generated
per each job that you run. Of course, there is some similarities, right, per tool. Specifically, for example, I can say that if I look at prime time cases, prime time tends to be a read-intensive workflow. If I look at VCS or NCSIM, it tends to be metadata-intensive workflow. There are a certain amount of similarities, but the gating factor became that when I was a customer of storage solutions, I would reach out to the engineering communities and say, hey, can you give me a test case? And they would give me 2 or 3 test cases. And what used to happen is that if I based my decisions on just those test cases, I wouldn't necessarily see any difference in production. And more often than not, even when comparing NAS solution A to B to C, or a storage solution in general, because Nick led in with a slide saying this is not just for NAS, right? But so, I wasn't really able to differentiate through synthetic benchmarking or even through specific test cases, which would just isolate a profile here or a profile here or a profile here, right? So I started exploring an alternative. That alternative was, okay, let me go on the NAS side and let me see what the NAS is doing and what the NAS is doing over time. And let me try to understand what type of a profile a given NAS is seeing and what another NAS is seeing and what another NAS is seeing in my environment. So I come from Broadcom, so I had access to a large number of different NAS systems, right? So I did exactly that. And I started looking at the consolidated I/O profile. And I said, okay, once I come up with the consolidated I/O profile, how do I replay it? And in that journey, I wrote my own scripts. I looked at SFS 2008, and that got me closer than my own scripts. And then eventually SFS 2014 in terms of some of the client-side implications, some of the mixing of the workloads, so on and so forth. So that's how we got to where we are. And so let's look at some traces to try to come up with this here, right? This is the goal here, is to come up with the consolidated profile. So let's look at one trace over time. And I actually had even more complex charts that I took out. So I simplified this. In EDA, most of the workflows are NFS 3, right? So you have over a dozen some RPC calls. If you were to condense that down, you condense it down to reads, writes, and others, right? And so you can look at this one over time, and you can see, okay, I'm doing this particular NAS is doing certain amount of read operations, certain amount of write operations, and certain amount of metadata operations. You can certainly see there are bursts of reads and bursts of writes, or bursts of metadata at least. There are certain bursts of writes, but you can't, in the scale of NFS ops, you can't really see it. And those bursts are actually important because that will skew the overall normalized profile that we formulate. But the idea became that if I strike a line through here, through the reads, through the writes, and through the middle on the metadata, then I would have some type of a EDA sustained average normalized profile over time, right? And the larger the sample you take, the better the results you get, right? And that's kind of the whole premise around how the profile was formulated. And if I improve a storage solution, what it's going to do is it's going to shift this chart up. It's going to give the ability of the storage system to be able to deliver a greater amount of these type of operations. The variation will not change, but the amount of reads, the amount of writes, and the amount of metadata that you can do will be shifted up through optimizations that you may perform, right? So with that in mind, let's look at the largest sample that I collected. I looked at 20 NAS systems that had been up for over 300 days. In aggregate, these 20 NAS systems had generated 1.84 trillion NFS operations. And I said, okay, what does the spread of those operations look like? So if you look at the entire NFS 3 stack, you have this type of a spread, 39% get adder, 23% writes, 18% reads, 12% access, so on and so forth. If you were to simplify that, you can say around 60% metadata, around 20% reads, around 25% writes, right? That's one EDA customer. Then I said, okay, let me rinse and repeat this exercise for over a dozen some EDA customers, because essentially they're all going through the same flow, right? So I did exactly that. And I said, okay, here's peer 2, right? Here's another customer. 41% get adder, 21% writes, 11% access, 8% lookup, so on and so forth. So the other chart was 59% metadata, this one's 64% metadata. 15% reads, 21% writes, similar, right? And so keep doing this, and so the rest of the slides are going to look similar, but there are data points from different EDA customers around the globe, right? So some are in Korea, some are in the US, some are in Japan, so on and so forth, right? So here's another one, 7 NAS systems, up 420 days, 188 billion NFS operations, strikingly similar, right? 64% metadata, 21% writes, 15% reads. I think almost identical. Of course, metadata is metadata, right? So you look at get adders here at 29%, over here is 41%. But when you think of it as metadata, it's 64% metadata. Of course, we factor in the unique characteristics of the metadata when we formulate the profile. Here's peer 4, 22% writes, 16% reads, 62% metadata. Peer 5, 65% writes, 16% reads, 19% writes. So on and so forth, right? So pie charts look pretty and they look nice, but what I did eventually is I tabularized them, which is coming up next. But just to kind of reiterate the point and emphasize the point, if you put peer 1, which is a US EDA house, and peer 5, which is a EDA house based out in Korea, and you put them side by side, and look at how strikingly similar their profiles are, right? 39% get adder versus 38% get adder, 10% access versus 12% access, 19% writes versus 23% writes, so on and so forth, right? Now you're getting into the noise level difference of 5%, and you can start claiming that it's 60 to 65% metadata, 15 to 20% reads, 20 to 25% writes, right? And so let's tabularize them. There is also some uniqueness at certain EDA shops which tend to blend hardware engineering workflows with software engineering workflows. So what this means is it means the chip design flow that I described to you is explicitly just the hardware engineering. It's the chip design process. Software is becoming more and more of a necessity along with the hardware. So a lot of these EDA shops have a lot of software builds as well. When you factor that in, what it does is it increases the metadata reads. So a lot of these metadata reads that are at 83%, 91%, those are shops that have a blend of hardware and software engineering workflows mixed on their NAS system. But the aim here for this profile that's being defined is specifically for the hardware engineering only. There is a software build profile already, right? So what I'm highlighting are the shops that are purely hardware engineering shops. And you can kind of see the trend there around close to 60% metadata reads on all of those, around 15 to 20% reads, and then about 25% writes, right? So that's the aim of what we're trying to get to when we try to reproduce this through SFS 2014. Any questions? I'm going to hand it back to Nick. Before I hand it back to Nick, any questions for me? Yes? File space. So like some of these samples were like the 1.84 trillion NFS operations that I talked about on 20 NAS systems. That was 640 terabytes, right? Some of the other ones would have been hundreds of terabytes. There was one other analysis that I didn't share with you, but irrespective of whether you take 200 data points or 2,000 data points, the net normalized average of the mix of operations comes out to roughly this much. Any other questions?
We saw a couple presentations earlier. What are the applications being served out in the world, right? What is the size of them? Where's it headed? HPC, I imagine, does this fall into HPC?
So, go ahead, finish.
Well, my question is, I guess, how big is this?
So EDA is a subset of HPC. If you look up HPC on Wikipedia, there will be a nomenclature called embarrassingly parallel. EDA fits into the embarrassingly parallel HPC in a sense that it isn't really truly HPC because the onus is left upon the end user to divide, subdivide, subdivide the task to have a job belong to only a core. So there isn't really much MPI being done. There isn't a lot of parallel processing. There isn't a lot of homegrown applications. There's only 3 application providers that are the most dominant. Of course, there's a 10% market for others, but Synopsys, Cadence, and Mentor Graphics are the 3 large application providers. And the way the chip design workflow has been done, and it's rightfully categorized as embarrassingly parallel because now they're running into this issue where there is a need to actually have parallel computing come into picture with the nanometer geometry. So certain flows are starting to fork off into kind of a multi-core, multi-host type applications, but it's limited. Any other questions? If you do have questions, of course, I'm still around after Nick.
So Jake has done a great job walking you through what the workload looks like. I want to talk a little bit about the motivation. Why do we want to make an EDA workload in SFS 2014? And Jake touched on a lot of these points. The commonly used tools out there or the scripts that Jake wrote himself, they're not doing a good enough job of representing production EDA workloads. And there are all these applications out there. Even though there's only 3 vendors, there's a lot of different applications for all the different job types. So there are all of these different workload profiles out there, all these different tools generating all these different workloads. And so, you really want to produce, like Jig mentioned, that combined workload that he has all these traces for. You want to produce that combined workload from all the tools in aggregate. And SFS 2014, I'm a little biased, but I think it's a pretty darn good tool for generating workloads. As we implemented the workload definition for EDA in SFS 2014, we stuck with the front end versus back end workflows. So the EDA workload is actually just consists of 2 component workloads. One is front end and one is back end. And this is because, like mentioned, there's a lot of small files doing the random I/O versus much larger files where it's sequential I/O. So it makes sense to keep those 2 profiles separate. If you averaged them out, you would get neither. So I'm going to throw 2 eye charts here at you. This is the front end workload. And you can see here we have the reads and writes. And the reads and writes are done as reading or writing a whole file. Because this phase is a lot more like a software build where you would pick up that file, that part of the chip, and you would incorporate it in something and then write a different kind of file out. So it's a lot more like a software build. So the I/O operations are all on whole files only. And we also see all the metadata here. You can see stat and access clearly stick out as large components, but there's a smattering of other types: create, make, dir, unlink to. We'll get to what unlink to means. Chmod, etc. And another interesting point here, you can see the average file size is 8K. So the file size distribution is centered at 8K, but it's a Gaussian distribution around that. Well, fairly Gaussian around that. Obviously, we're not making incredibly small 1-byte files. That would be a little bit strange. Another thing to point out, the geometric is set to 50%. The finer details of that are a much longer discussion, but that means that 50% of the time we're going to follow a geometric distribution when selecting what file to use. So basically it means you're going to get either, call it hot banding, call it file selection skew, just call it skew. There are going to be files that are accessed a lot more than some other files. But there's still going to be a background workload where there's a random distribution of files that could be chosen as well. So it's a layered approach to generating this sort of skew, if you will. You can see the I/O sizes are much smaller for reads. You know, we're somewhere between, well, 1 byte and almost 32K. Writes are even smaller at the 1 byte to almost 8K range. And that's all I'll point out. There's a lot more details here, and this will be in the user's guide when we release this workload. And it's in the slides you have, of course. The back-end workload, you can see here we're all sequential reads and writes, because that's what these tools do. It really is either it's sequentially reading in something and then sequentially writing out a result. Here again, we do have that same skew parameter set to the same parameter as the front-end workload. So I thought I'd point that out. You can see the I/O sizes are much larger. Reads here between 32 and 64K, and the writes are between 32 and 128. And the files are much larger. Average file size here is centered around 10 megabytes. And I will say, everything is subject to change.
So the only thing I would add here is that for both of the profiles, the read and write transfer size distribution is actually based on traces, actual traces from the NAS systems.
Yeah, there were even more details than we could show you in the time we have. Yeah, everything is based on traces, and we've been replaying, and we're still testing to make sure that the workloads that is produced matches what we see in the traces we have. So I wasn't sure if I'd be able to do this, but I did. This is not an official SFS 2014 result by any means. It's just an experiment. You can see it's a generic Linux NAS server, and it's just example data. But I took a generic Linux NAS server, CentOS 7.2, and some clients, and I ran the EDA workload as we've defined it in the previous slides. And you can see we get, a fairly standard operations per second versus latency curve. In this case, we're SFS 2014, so we talk in terms of business metrics. But you can see even this generic Linux NAS server was managing a respectable 31,500 operations per second at a decent latency. Obviously, we can see, we have a standard knee of the curve, but things are looking well behaved, sort of reasonable NAS type performance, like you would expect. And this was NFS v3. So this is your typical EDA shop. And then just to be weird and confuse people, I thought, well, hey, I have a Windows environment too with a Windows NAS server. Let's run it on that. EDA with SMB3. What do you think, Jig? We're going to see that? Regardless, I ran it, and you can see, overall, it achieved a little less. It did have fewer disks on the back end, but we got a somewhat normal curve. You can see, obviously, we have a very steep, very sharp knee, but again, we did wind up with, 27,000 operations per second, again, with a respectable latency. So, even with the workload in this pre-release state, we are seeing reasonable results coming out of the benchmark. So there may be a little fine-tuning, but we're well on the way. So currently EDA is the anchor feature for the SP2 release of SFS 2014, which is what we're working on right now in the subcommittee. This is going to be a performance neutral release for all the existing workloads. So this means that all the currently published SFS 2014 results are going to remain valid and comparable to any future results. We're not up-revving the benchmark in the major version. So everything stays the same, everything's performance neutral. Otherwise, we would have to up-rev it. We don't have a choice on that. It's a standard benchmark. And because of this, there's going to be no distinction on the results page between SP1 and 2 results, because there's no need. And the upgrade is expected to be free for all current license holders. So in addition to EDA, we're also adding some other features. We're constantly adding things to the workload generator because we use it for vendors use it for custom workloads and their own regression testing. So we're adding some features that we thought were interesting and didn't affect the performance of the official workload. So among those is an unlink 2 op type, which is just unlink that removes files of size. Previously, unlink only removed empty files. We are also adding dedupable dataset options, so the ability to generate a dataset that is dedupable. Previously, all files were undedupable, but you could and we did set the compression ratio. And because dedupe is one of those things where the implementations vary greatly by vendor, we are adding granule size options. You can set that dedupe granule size based on your platform. We're still working out all the details on what that means for standard workloads. But the options will be there in this release to at least play with internally for engineering purposes. And because we gave you the option to set a dedupe granule size, we obviously are giving the option to set a compression granule size because, well, if your compression granule size is bigger than your dedupe granule size, you will probably not get what you expect, as you may be able to figure out. Another thing we added actually for the EDA workload was the ability to have different file size and directory, different numbers of files, numbers of directories, and file size distributions per component workload. And we needed this because, like we've been saying, the front end and back end workloads are very different in terms of the files that they access. And previously, we didn't have an option to set these per component workload. Now we do, and we take advantage of that in EDA. All the existing workloads, of course, are unaffected because they have to remain the same for comparability. We are adding a flag so you could have an encrypted data set. I'm going to leave it at that. It's sort of nebulous, but it's an interesting interesting encryption algorithm. I believe it's the one that Don Capps, the author of NetMist, actually came up with on his own. We're not using that in any workload right now, and it's not going to be enabled for EDA, but it is an interesting thing to test. Also, we've reduced memory consumption. This is especially relevant for the software build workload. We just found optimizations and put them in because why use memory when we don't have to? It makes testing a lot easier. Sort of the key takeaways, well, EDA certainly is it's a unique and interesting workload. Initially, you may think, well, it's just software build. Who cares? But software build has a little bit more metadata, maybe a lot more metadata depending on your scale, but it also does not have that, those large files with that sequential workload, like the front end, or excuse me, the back end workload has.
Basically, the ability to mix workloads is the key here.
Yeah, having that mixed workload. So it certainly is unique, and we have a very large number of traces, like you saw, with many, many ops from many different vendors across the globe available to us, and that's a way to make a really nice workload. So we do plan to include the EDA workload in our next release of SFS 2014, and that release is expected to be a free upgrade for existing license holders, and it will be performance neutral, so all results remain valid for the existing workloads. We're just adding a new one. So that's all the slides we had. I would like to take a moment and note that we do have some publications up. Some vendors have submitted results for some of the SFS 2014 workloads. So if you haven't had a chance to review those, I encourage you to. They're very interesting, especially you can compare GPFS to ZFS. And that certainly was the goal when we were making that benchmark, to encourage stuff like that. Because it is the same workload at the application level, of course. That's the whole point. And the other thing I'd like to mention is just a plug for SFS. You know, if you work for a fairly large company, chances are you're already a SPEC member, so you are free to participate, or we encourage you to join the SPEC OSG organization, and you can have input into these workloads. And we love input. You can help develop the benchmark. You get access to the latest and greatest stuff for your internal engineering testing, and the scary part is we have to help you get it running. So we to do that if you buy it too, so you can do that too. But so I encourage that. Also, if you're a customer of a large storage company, I would say ask them for their SFS 2014 results. It is an industry standard benchmark for file access. So the best way to get submissions is to have customers ask for them. So sales pitch over. Any more questions? BP, what's going on?
So what's the compressibility? Sorry, how do I say this? What is the data set compressibility for EDA?
So the question was, what is the data set compressibility for EDA? And we could roll back. I'm 99% sure that's set to 50% for both sides, and Jig can speak to the derivation of that.
So the dedupability is about 40%, and the compressibility is about 50%.
About?
Yes, correct. Right.
I hate about, by the way.
And you'll note I didn't actually put any dedupability stuff on here because that's still under test, and I know that I have the disclaimer, but I really don't want any of that set in stone.
when it means,
we're still qualifying.
when we talk about, right, it's when we talk about reads or writes. For example, reads are of a range 15 to 20%, writes are of a range 20 to 25%. So similarly, when we talk about compressibility, it's like, hey, it's 49%, 52%, 53%, so on and so forth, right? So it's in that range, right?
BP's pondering.
No, I haven't.
Somebody's going to publish two numbers, one for front end, one for back end, or is this a combined workload?
You can only publish the EDA as a whole. The component workloads, you can't separate those out and publish them. If you wanted to, when you have a copy of the benchmark, you could separate them yourself and run them separately if you wanted to. It's a fun exercise. But you could only publish EDA as a whole.
So you intend to running both workloads in parallel?
Exactly.
Right, and I mean, that's what the EDA production house would be, that's how the EDA production houses would be exercising the storage.
What are the typical file sizes? If I may understand.
So the typical file size is 95% of the files are less than 100K. 95+% files are less than 100K. 5% of the files are 0 to 5% of the files are greater than 100K. And I have an entire breakdown of the file size spectrum. And so what we did is we actually mapped the Gaussian distribution that SFS 2014 does, and we figured out where would we center the front end and where would we center the back end to get to a similar file size distribution that we're seeing at EDA customers in terms of the percentage breakdown. And it actually boiled down to the point where we actually needed to drill deeper within the sub 8K files to say, hey, exactly how many percent are 1K and how many percent are near 8K, so on and so forth. But that's factored in as these profiles are generated.
Yeah, look, it looks very simplistic with average file size 8K, and that's how it's defined. But you know, we did actually look at the distributions of what it produces, and they were
right.
very
So what you
close.
would do is you would run NetMist or SFS 2014 with the 8K distribution, and you would say, okay, how did it lay that out? And you would also compare that with the 10 meg on the back end, and you would look at the entire data set, and then you would compare that to the production data set.
Any other questions? Yeah.
If possible, I have a question in general about SPEC 14.
Yeah.
So you've told us that it doesn't generate stream of request itself, the protocol itself, and works on top of file system.
Mhm.
Doesn't that file system
So the question is, since SFS 2014 generates workload at the application level, it's going through, it could go through different file systems, and won't that affect the results, and will they be comparable? And the answer is yes to all of those. The main point we wanted to make, well, there are a couple things. First of all, it's very difficult to get the development resources to write a piece of code that will generate every single protocol and version out there right now, especially as SMB has gotten so mature in the past several years. You can barely keep up. The Samba team can barely keep up, and they're huge. Well, they're not huge, but it's a lot of brain power behind that team for sure. And the other thing is, it's sort of more interesting to us to do what the applications would do and let you see, okay, if I'm running ZFS, this is going to happen. If I'm running on GPFS, this is going to happen. Because we could never have done GPS if we're trying to write a protocol, right, directly out onto the wire. Like, we'd have to write InfiniBand that looks like I'm sure it's possible. But, so the end goal is that the result you measure is the result you would get if you ran that sort of application with that sort of whole storage stack. And so is it comparable from one vendor to the other? Well, if I ran with CentOS 6 and on my array, and then NetApp ran with CentOS 7.2, there actually could be some differences there, and that is an annoying case where it's like, well, okay, did Linux change, or is it a Dell EMC versus NetApp thing, or something like that? So we had to take that bad with the good of the whole testing that whole application stack and getting people the answer that they would really get if they ran that application in that whole environment. So it's a balancing act. It is a bit of a compromise, but I think from the testing I've done, I think it's a pretty good compromise.
Just a comment.
Yeah.
I'm actually, I don't worry. We'll observe that more than NFS client stack differences say, if you're running over NFS, never mind, elephants compared to oranges on different file system types, the amount of memory in the client has a remarkably large effect where it had zero effect for all intents and purposes on SFS 2008, which is unrealistic. So lots of memory will basically provide massive caching when it can cache for the applications and give you a better predictor of what a application might see due to investment in memory.
Yep.
Or whatever
So the observation was that, having tons and tons of memory in your client versus very little memory in your client will affect the results and inflate them because of all the caching that's possible. And yes, that's certainly true. And we can't get around that. And perhaps...
But nobody in the real world can get around that.
Exactly, yeah. And nobody in the real world can get around that. Turn this way. But I think a good note to make everyone feel a little bit better about that is that we do have a disclosure form. So the examples I showed were, where were those? So this is like your first browser page. It goes on for many, many more. And you have to disclose, what you used to generate the load, the characteristics of it, the amount of memory. The amount of memory is actually totaled for the whole storage solution. So if you have a terabyte of memory in all your clients, and you have 256 gigs in your storage array, and that's what you're trying to sell, we're relying on the customers to be smart and review these carefully, or the media to do it, or marketing departments to, point out what the other guy did, right? And so your total memory would be, some massive amount of terabytes versus someone who used a more normal config or a smaller config anyway, where they would have like a terabyte or something like that.
So I'll also put a little bit of a customer side spin on it, right, or a EDA end user consumption spin on it. I actually used to model the EDA workload using SFS 2008, and that gave me exactly what Brian's talking about in terms of not having the client-side caching effect. And I presented that to many EDA customers, and they actually argued against that, saying that, well, no, I do want my client-side caching behavior to be factored in as I try to judge the performance of a storage system, because that helps me determine how I would size it. So as you think about this workload specifically, what you would want to think about is you would be sizing your clients or solutions for the EDA storage to be similar to what EDA customers would have their client memory size to be in the compute grid.
Yep. I think we're being politely told our time is up, but appreciate you coming out and all the questions, and be sure to grab your spec pen if you haven't already. So we'll be around, Vern and I at least will be around all week, so any more questions. We have one more session about Emerald, so feel free to stop by or catch us before or after that. Thank you.
Thank you.